Students, we're going to do a little bit of sketching on the document cam. Unfortunately, it's not going to be a talking PDF, but what I'll do is I'll be using some regular notebook paper and a regular pen on the document cam in a few minutes. And then what I'll do is I'll embed that in the YouTube, and I've got slides set up for that. So you'll be able to see everything in YouTube, and you'll hear me, blabbing my narration in YouTube. So it'll be good, but that'll make it a little bit slower for me to do my YouTubes. So it might be a little bit later in the afternoon when we get to that. A week from today, exam 3. As you know. And this is the one that you really want to crush, because if you can crush exam 3 like a bug, everybody in here, I want you to shoot for, and some of you guys are starting to blaze upwards. It's great. But I want everybody to crush it like a bug, because then if you have 3 on the books, then we drop the stinkiest one if you've got a bad one. And we keep the best 2. So that's what we want to do. You want to be in that position. All right? In regard to exam 3, for which the same exam procedures will hold, there will be next Monday morning, 9 to 10:30, SI review with Maria, so you can get up to speed with that. Also, for those of you that, let me just go back a slide here. Office hours, Wednesdays, 11 a.m. to 1 p.m. And last week we just talked about grades and stuff, but if you want to come to office hours tomorrow and work out, just figure out that thermal equilibrium, and this time for sure, 11 a.m. to 1 p.m. In the Physical Sciences building, which, if you know where the Student Health Center is, just keep going down towards the shuttle bus stop, and that's the Physical Sciences building. It's like, there's Student Health Center, then there's Counseling Center and Libra, and then there's the shuttle bus stop, and that's the Physical Sciences building. So, and we'll be in room 158. Question in the back. Homework 8? Homework 18, question number 8. What one was that?
It was the one where you had to choose 1 through 5, and then you had to put which one of these determines the vibrations throughout the waves. And I couldn't have sworn it was all 3, and then I tried, maybe it's just the vibrations.
Yeah, now what was the answer to that one? Do you recall? I know the question. There was 2? You know what? I think it was 1 and 2. And was it just 2? Okay. All right. Because I tell you what. Here's what I want you to do. What is your first name again? Juan. Juan, what I want you to do, this is good, and I'm not ready to discuss it right now. But what I want you to do, this is like, James Bond, he has a license to kill. Now I'm giving you, Juan, a license to post something in discussions, and you're the only one that can do it, just like 007, in times of danger. Okay? So Juan, I want you to post in discussion a question about that one, and we'll go over it there, okay? And I'll talk, and Austin obviously knows the answer. He's the expert on it. He can post. And anybody else that feels good about it, if you get in there before I do, more power to you, all right? And in general, that's what you should be doing, before the homework is due. Post questions like that. But please do that, Austin, and that'll be helpful. Okay, so anyways, getting back to the prep for exam 3, office hours tomorrow. And if, and what we do at office hours, whoever comes, if they have a question, like number 8 on homework 18, we talk about it. And if it's a calculation, like thermal equilibrium, we go to the marker board and we just work it out. And the student is at the marker board operating the marker, and I'm sitting in a nice comfy chair coaching you, and whoever else is there is coaching you, and we just work it out 50-50 right down the middle and get it squared away. All right, so that'll be all. So, and think about office hours as studying with Dr. B. If you think of it in those terms, it's going to be really helpful. If you can make it. If you can't make it, you can't make it. But if you can't make it, then you post in discussions like, Secret Agent 007. All right. Okay, so SI review, also good. Try to get going on that. Now, I am ready to talk about homework 19. I want to go into homework 19, the oscillator energy questions. All right, and they constitute part of our lesson for today. And what we're trying to do here is find our way into the periodic table, which we'll do after Thanksgiving. All right, and we're putting in just the last few little cool concepts before we can really blaze into the periodic table. All right, so now last time we looked at the potential energy of the harmonic oscillator. By the way, go ahead and write that down. Simple harmonic oscillator. That spring system, if you think of that spring system as an oscillator, and if you idealize it to having no friction, just a spring force, then its name is simple harmonic oscillator, SHO. All right, and one of the things about the simple, here's the picture of it. Here's a picture that I've used. We'll use this picture through today's lecture. The force depends on the displacement, the potential energy as well, and the potential energy depends on the displacement and actually the square of it. All right, and it's symmetric left or right of equilibrium. So if you go 10 centimeters to the right, and measure your potential energy, you'll have the same potential energy if you go 10 centimeters to the left if you can, if you don't run into a wall or something like that. All right, so for that reason, the formula is this special one, 1/2 kx squared, and we're actually going to talk about that particular formula on the document camp when we get to it. Because it's really, I'm going to show you something that's kind of cool about this, plus the kinetic energy. All right, so the kinetic energy, that one that's something that we've been using for weeks now. It's good old 1/2 mv squared. And we talked about that last time. And your homework, I just gave you the total mechanical energy formula. That's pretty simple. Here it is. Down here in flaming letters, 1/2 kx squared potential energy plus 1/2 mv squared kinetic energy. And I want to draw your attention to something here. Does anybody see kind of like an overbaked momentum in there? It's not, there's no momentum in there because it's all energies. But do you see like kind of what do you see? Yeah, we got an MV in there, except it's MV squared. So, and what we're going to do on the document cam, we're going to convert that into a statement about momentum. Okay, it's 1/2 mv squared now, and in a short while, we're going to turn it into a statement about momentum. Now, the interesting thing and useful thing about it is, if you can figure out the potential energy and the total energy, Well, if you know like the spring constant, K, the spring constant is newtons per meter. You know, how many newtons does it take to go 1 meter from equilibrium? And then the mass, if you know that, and you pick a position, you can figure out the total energy and the potential energy. All right? And if you know the kinetic energy, so if you like take it and you want to put it at maximum compression, like right here to the left, yeah, no problem. You can get that. Figure out, if that's the maximum compression, then that means that you can't push it any further to the left in this direction. So it's stopped. If it's stopped, its kinetic energy is 0. Are you listening? At maximum compression, kinetic energy is 0 by definition. Maximum compression means stop. You can't compress it anymore. So you're stopped. It's a turning point of the motion. So kinetic energy is 0. Potential energy is maximum and equal to total mechanical energy. Question?
How do you see maximum compression on the graph? Like, will that be on the test?
I'll tell you, yeah, I'll always spell it out, what maximum compression is. And this one, maximum compression is 10 centimeters. It's kind of hard to see in this diagram. You won't need this. I'll be spelling everything out for you in just a minute. But, yeah, on this one, it's 10 centimeters left, negative 0.10 meters. And max extension is out there. Oh, sorry. I'm sorry. I read it wrong. It's minus 18 centimeters, minus 0.18 meters. And then max extension, I'm a little closer. I can see it. That's 18 centimeters in this diagram. And I'm going to be asking you some clicker questions in just a second with this diagram, but I'll be spelling out all the coordinates and stuff for you to use and stuff. So, but anyways, that's where we're heading for. All right. So if you want, total energy out there, do it. If you have some other point, some intermediate point, like 10 centimeters to the right, do it. All right. You can figure out everything. And you know what it's like? It's like those free fall energy tables. Once I tell you that you're dropping it from a certain height, that means kinetic energy is 0 at that height. And potential energy you can calculate above the gymnasium floor. And so that's equal to the total mechanical energy in the far right column. And then it's dittos all the way down from there. Remember we did all that? You can do something similar with the left-right motion of a simple harmonic oscillator. Now, what we're going to do is right now we're going to work through multiple choice and then calculation, a kinetic energy and then a moment. Actually, we're going to do a speed calculation. But once you get the speed, you can figure out momentum, just multiply by the mass. All right? So get your clickers out and definitely jot down these specs, because this is the preamble for all of the next 4 or 5 questions. Your spring system specs. R, spring constant, K equals 120 newtons per meter. So it takes 120 newtons of pure force to bring that spring out by 1 meter. Now, we're not going out a meter, but if we were, that's what it would take. And the mass on there, that big block, is 0.240. Now, we're focused on max extension. You pull it out to 0.18 meter wand, and you hold it there. Okay, so you're holding it there. Kinetic energy there is 0. So what's the total energy? Total energy, all potential energy. Go ahead and calculate. Let me see what you guys have got. Dun, 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 dun. You've got multiple choice here. So Just go back to that total mechanical energy equation. E equals 1/2 kx squared for potential plus 1/2 mv squared for kinetic. Now, if V is equal to 0, as it is here, you don't even have to worry about that one. So all you have to do is calculate the only thing remaining. You guys are doing good. Ooh. Yeah, so this position is it's 18 centimeters, but I want you to work in meters. So work it as 0.18 meters for your X. And I can see you guys voting. Okay, 45 seconds. Nice. Good. I see you guys consulting with your neighbors and stuff, which is good. Remember, you always want to, during a clicker question, especially a tough one, talk to those people that are around you. If they're not wearing earbuds. If they're wearing earbuds, you can talk to them, but they might not hear you. Okay, so A, B, C, or D. Okay, 15 seconds starting now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Raise your hand if you got 1.944. Sweet. All right. Now, that's ditto marks. You know, well, let me go to the next question, if it please the court. What's the total energy at x equals 0.10? 10 seconds to vote. 10, 9, 8, 7, 6. Okay, I'll give you a little more time. Read carefully. Different position. So you let it go and you snap a photo. Okay, now we're at 0.10 meters. We're in that intermediate position for where this diagram is set up. Okay? So we figured out E at max extension. Nice. What's capital E? Total mechanical energy at this intermediate position. 10 seconds to vote. 10, 9, 8, 7. Wait a minute, I better grade it first. Fortunately, you guys are geniuses. You're starting to learn this stuff. Gosh. 10, 9. Okay, now I'll give you 20 seconds. Starting right now. 20. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, get that vote in. Raise your hand if you voted for 1.944. Good. That's the right answer. This is your ditto marks. This is your first ditto mark. And any other position you care to, as soon as you set up the system, your initial conditions are x equals 0.18 meters, v equals 0. As soon as you set that, you got the total mechanical energy everywhere else. Now, at some other point, like 0.10 meters, you may have to calculate kinetic energy and potential energy. All right, that's just like the free fall, potential energy and kinetic energy, different levels of the table. You got a little bit of both. And that's what we got here. So let's do the next one. Spring potential energy at 0.10 meters. And let's go to the next question. Okay, go ahead and vote. Do 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 do. Na 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 na. Well, I see that I'm... you guys are... Man. You guys are blazing. I think this is the genius section, actually. No, seriously, because I think you guys uniformly get better grades than those guys in the second lecture. It's not hard to understand. They come in and... you guys are coming in, you're alert. You're drinking coffee or stuff from Starbucks, right? And those guys, maybe you have some Cheetos or something. Those guys, they're coming in from Chick-fil-A, so they just had a bunch of French fries and nuggets and stuff, so they're not really, it's gonna weigh down their mind. So that explains why they're not so sharp. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2. Come on! All right, that's better. Waiting for you guys to get your votes in. Okay. So for this position now, intermediate, nothing special about it, just 0.10 meters. The spring potential energy, 0.6 joules. Go ahead and raise your hand if you got that one right. Okay, now, the total mechanical energy, 1.944. We already figured that out. The potential energy, 0.60 joules at this position. We just figured that out. All right, how much kinetic energy have you got? Let's get this one going. Oh, Lord. You guys, I'm going to have to start getting up earlier, I guess. You're just too smart. You're blazing. I just challenge all you guys. You guys are doing good on this. This is not easy stuff, but you guys are doing good on it. And I just challenge you to think, would you have expected to be able to handle an oscillator? In August, when you came in here on August 20th, I'm going to know how to do oscillators here in a few weeks. You would have never thought that. But you know what? Physics majors would be getting tripped up on this. But you guys are not getting tripped up. Oh my goodness. Okay, 20 seconds to vote. Starting right now. Brittany. Nice. Good. I love seeing you guys helping your neighbors and talking things over with your neighbors and whatnot. Because it means you're thinking. 149, 2.8. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Come on, you guys. All right, there we go. Who voted for 2.544? Don't raise your hand, because that's not the right answer. And 93% of you guys voted for the right answer. All right. Now I got you right where I want you. So make sure you write down K equals 120 newtons per meter. Make sure you got that in your notes. And mass equals 0.240 kilograms. All right? So that's half a bottle of water. Same mass as about a half a bottle of water. All right? Kinetic energy, 1.344 joules. All right. Now hit the refresh key. We're going to calculate the speed. And you know how to do it. We've done this before. If you know the mass and you know it's 1/2 mv squared, ding. Just got to do a little bit of work to get your speed. All right? So you ready? Let's go. Same oscillator system, same location. Hit the refresh key. Better hit the refresh key again, and then I'll be looking for a number now. Give me to the nearest 1/10 of a meter per second. And this is really all you need to do in order to figure out momentum. You figure out V, and then you already know the mass, so m times whatever you get here is the momentum. Good, good, good. La da dee, la da da dee, la da dum. You take the high road, and I'll take the low road. And I'll be in Scotland before ye. Okay, make sure you hit the send key. And be careful with that decimal point. I think everybody's doing their decimal points pretty good here, though. Ugh. Kwame, where you? Good. 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 Kwame, you getting it? Good. Juan, you got it? Let's see. We'll see in a minute. Okay, 1 minute, starting right now. Yo, are you double checking their numbers? Yo, you double checking? Yeah, good. I just saw some guys over here doing the same thing, so that's good. Yeah, double check your neighbors' numbers. If they disagree with you, double check. Maybe you made an error, maybe they made an error. You can't do it on exam day, but... Oh, did I say exam? Midterm exam 3? Kinetic energy? Simple harmonic oscillator? Oh my goodness. Oh my goodness. Oh my gracious. I'll be in Scotland before ye. Na 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 na. Okay, this time a minute. This time for sure. "45 seconds. "30 seconds. New, new, new. New, 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 new. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Come on, you guys, get that number in. Come on. Move it. All right, you don't want to type in your number. Let's see what we got here. Uh-oh, I see one person rounded off wrong. Raise your hand if you voted for 3.3. Good, that's the answer. And I know I see one person typed in 3.4, so they made a round-off error there. But 83% of you got it correct. Now, I'm going to go to the document camera now, okay? And I'm going to review this calculation, okay? And then we're going to do a little bit more with the harmonic oscillator energy equation. So let me put this over here to the side. And I'm going to keep recording into the YouTube, but I'm going to switch displays. Let's see if we can do this gracefully. Okay. Okay, here's our layout. And our point of interest is right here, 0.10 meter. So this, I'll just put a dot here to represent the mass. So it's moving to the left, okay, and it's got some speed, and that's what we're trying to figure out. Now the 1/2 kx squared is right here. All right, and we figured that out. That's 0.60 joules. So the kinetic energy here at x equals 0.10 meters is equal to 1.344 joules. Okay, so, and that's equal to 1/2 mv squared. So 1.344 joules equals 1/2 times the mass, which was 0.240 kilograms, times my v squared. So I got to figure out v squared, and then I got to square root that and get v. All right. So, okay. I'm going to change this to 1.344 kilogram meter squared per second squared, because I'm going to cancel here in a second. Okay, 120 kilograms. Okay, so 1/2 times 0.240 is 0.120 kilograms, and here's v squared. Okay, now I'm going to cancel kilograms. Bing, bing. And so my v squared now equals this junk over here, 1.344 meters squared per second squared, divided by 0.120. And notice that I don't have any units down there in the denominator. That's good. I canceled the kilograms already. But if you didn't, you could cancel. If you still had kilograms top and bottom, you could cancel them right now. So either way, you're good. All right, so now that's v squared. So we just got to figure that out. What's 1.344 times or divided by 0.120? So that's going to be about 10 point something or 11 point something? 11.2. Give me 3 decimals. 11.2 even? Yeah. Sweet. Okay, so that's meter squared per second squared. You know, I didn't even design it to be that way. Okay, so V is the square root of that stuff. 11 points, so that's going to be about 3 point something. Yeah, so 3.3. So there's how you get that. To the nearest tenth anyways. Now the momentum, you can now say, okay, P is 0.240 times that. And what does that work out to? That's about 0.8 something. 0.792. Has anybody got that? 0.792? Okay, 0. So let's write down 0. Is this good? 0.792 kilogram meters per second. So you can always get, potential energy and, from position, and then if you have E, you have everything else you need. Speed, kinetic energy, and momentum. Now, I want to bring something up to you. Here's our equation for total mechanical energy. Okay. And I drew your attention earlier to the fact that we actually kind of have a hidden momentum in there, in the kinetic energy term. All right? Now, we know that P is equal to mv. And I've got an m and a v squared. So P squared is equal to m squared v squared. All right? So that's nice. But I want to divide out a factor of m. So P squared over m is equal to mv squared. All right? And so this formula here, let's go to the second page of the document camera files. Got all these little fringy things. So what I'll do is I'll scan this into the PDF scanner and then embed it in the YouTube. All right, so let me bring this down here. So E equals 1/2. Now we're going to leave 1/2 kx squared by itself. And 1/2 mv squared, we're going to change that. And here we go. 1/2 kx squared as before, plus 1/2, and then mv squared is this stuff here, p squared over m. All right? And so let's write it down so that it looks nice. 1 over 2m times p squared. And that, my wonderful students, is a significant result. Because now we have a position and a momentum that are both second power. And that is something significant for us, and I'll show you why in just a minute. First question from Connor.
Well, sure, I was going to ask whether it's advantageous to know, but I thought you didn't tell us.
I am about to tell you why it's advantageous to know this. But before we do anything more, let's divide both sides by E. Let's get a 1 over on the left. So we're going to get a 1 and a 1 over 2e times kx squared plus 1 over 2me times p squared. All right? And so now, this formula here, my wonderful students, is now a formula for an ellipse. In phase space, where we map out the position and the momentum. All right? And that is going to be significant for us. That's the significance, Connor. Because if you go back to like sophomore high school geometry or maybe 10th, 11th grade trig or so, you remember that the formula for an ellipse in xy coordinates is x squared plus y squared, each divided by a different number, equals 1. And then if you have this, then it tells you that your ellipse fits in a rectangle like this. Now that's on x and y coordinates in high school geometry. All right? Now what we've got here is an ellipse in phase space. All right? And so let's do this out a little bit. And what it's telling you is that go out here, maximum extension. Maximum compression, we'll call this minus x1. All right, try to make those two distances the same. And then I'll go 3 units up. This is maximum P. And we can figure that out. Where's the momentum maximum in the spring system? At max extension, max compression, or at x equals 0? Where's it moving fastest? Think. Where's it moving fastest? Right, it'll be moving fastest at x equals 0. So this point up here, and this point, this is minus P max. 3 units down, it's going to be all symmetric. So you can gracefully trace in, as gracefully as you can. Well, that's a little wobbly, but on my computer I can make it really sharp looking. All right? So that's an ellipse. If you know this, if you know x1, max extension, or similarly, if you know this over here, max compression, you can figure out everything else if you know K and M. Now, K and M and capital E encodes maximum extension because capital E is 1/2 K x1 squared at max compression, max extension. Either one. Okay, so this denominator up here, 1/2E, that's actually got a max compression, max extension squared in it. So if you can get that, you can figure this out. Now, third document cam. We're doing good. Okay, so this is number 3. Let me draw another. You go ahead and just keep the diagram that you've got. And I'm going to draw in okay, so there's my box for my ellipse. And let's see if I can. It's supposed to be perfectly vertical, left and right, perfectly horizontal here. But it's kind of hard to, there's a pretty good one. It's kind of hard to do it by hand, but and make it really good and symmetric. That's a way better one. Okay, so I'll just put the letter E here to symbolize that's the ellipse in phase space when the total mechanical energy is E. And I'll call it E1 because I'm going to do a second energy state. Connor.
So this is supposed to be an oscillating system too?
It is an oscillating system. It's a simple harmonic oscillator. Now, I'm going to draw another bigger ellipse. See if you can draw one. I'm going to make mine a little bit bigger. Parallel around this one. You know what I need is another color ink pen. Actually, I'll just make it solid. So this is E2. So this is another energy. And E2 is greater than E1. So if you have something that's oscillating, Connor and everybody, But, if it can have a higher energy, in other words, you pull it out a little bit further than 0.18. Pull it out to 0.19. You'll have a higher energy, E2. So this might be where the ellipse is. Okay? And you can always draw out your ellipse. My wonderful students. Electrons orbiting the nucleus, they're an oscillating system. You can map out the electrons around an atom with this diagram. And guess what for atoms, the difference let me give you one more formula here. I'll put it down here. The area is equal to pi times A times B. So A is the horizontal, half the horizontal width, and B is the half the horizontal, or half the vertical. Okay, so this is A1, and this is B1 up here. The area is easy to compute. The ellipse is easy. The area is easy. In an atomic system, the difference in the areas is a multiple of Planck's constant, h. So now you know the rest of the story. Planck's constant comes in with oscillating systems if you look at their ellipse in phase space. And the periodic table is explained really nicely in terms of this diagram right here. Different energy levels for an oscillator, an atom, different ellipses. And the difference is always some multiple of Planck's constant. Connor. And nobody knew that. Planck never knew that. But we know it. We figured it. You know who figured it out? Einstein and those guys. A little bit after Planck. Go ahead, Connor.
Well, I'm sorry, I don't quite follow. What is this telling us? And what is phase space?
Phase space is an abstract space where instead of mapping out X and Y like graph paper, east and west, north and south, you map out the abstract values of the momentum. You can't take a picture of momentum. Where is it? Things have momentum. You can map out its X coordinate. That's easy. So this is an abstract space. It's used for analyzing motion. Cardiologists use it to analyze the motion of your heart, to make sure if it's a good sinus rhythm. A good sinus rhythm will give you an ellipse or even a circle. All right? And the reason that we use this, Connor, is because, as I'll mention after exam 3, so the last week of the semester, no one knows why nobody initially knew why atoms were quantized. Why is there any kind of a quantum system in nature? This diagram explains it perfectly. And what we find with atoms is the electron can, in a hydrogen atom, for instance, it can't exist at any elevation above the nucleus. If we have a spacecraft orbiting Earth, it could be any height we want, 200 kilometers, 500 kilometers, 501 kilometers, anything we want. It's a gravitational system, no problema. Atoms, no. You can have a certain radius and no other until you get out to a little bit bigger radius. And the energies change. And the changes in the energy, because it's closer to the nucleus. And so those energy changes for different orbits are perfectly explained with this diagram, because the electron in a higher orbit behaves differently, and it produces light that we'll see two Tuesdays from today. I'll give you a demonstration of the light produced by pure hydrogen. And you'll see how energy levels and light are all mixed up. And this is the thing that explains it visually.
The difference in area is Planck's constant, is that it?
Yeah, or a multiple thereof. So 7 times Planck's constant, or 1 times, or 22 times. And phase space is naturally measured in units of Planck's constant. And if we ever you may have heard of quantum computation and quantum electronics. If we ever get that perfected, everything that those guys do, they're always thinking in terms of units of Planck's constant. So, all right. Now, I want to talk about some more stuff here. We've got 15 minutes. Interference of waves, we've talked about this already a little bit. I want to try to finish this up today. And we've talked about diffraction. And basically, with interference in general, what you want to think of is the source. Two different sources. So like a storm off the coast of West Africa and a storm off the coast of Nova Scotia. Now they're both going to be sources of ocean waves, but they're going to go off in different directions. And where they meet, they interact. Okay? So the waves move out independently from each source, and at certain points, like out in the middle of the ocean, you might have 2 wave crests meeting. And that would be a super big crest. Or if it was at the coast, it'd be a super big surf. Or out in the middle of the ocean, it'd be a rogue wave. Now, at other points, you might get 2 troughs that meet at the same point. So one of your waves coming from the coast of West Africa and one of them coming from Nova Scotia, at some point, 2 troughs are going to interact. And in fact, a lot of troughs are going to interact. But you look at 2, and when they meet at the same point at the same time, you get an extra deep trough. Okay, so that rogue wave is an extra tall wave and an extra deep trough right next to it. All right, so it doubles the amplitude. Now, that is known as constructive interference. All right, constructive interference. There's another kind of interference. And just imagine, 2 storms, one off the coast of West Africa, one off the coast of Nova Scotia. And let's say that a crest and a trough interact at a given point, at a given instant of time. If that happens, you have no wave, you have flat water. And that is known as destructive interference. For that instant of time, at that position, you get flat water. You have you don't say that there's no wave, but you do say that the waves cancel. They destroy each other for just that moment of time. All right, now that's an outline with some sentences. I'm going to give you some pictures. Brittany. Oh. Thank you. Slight detail. All right. All right, here's what I was just talking about. Good one. You should have said this 5 minutes ago. Gosh. I'm blabbing my big mouth up here. No pictures. Anyways, so constructive interference, that means you've got peak to peak, or maybe you've got trough to trough. So you get peak to peak, you get an extra high peak. Double the amplitude, or whatever the sum of the 2 amplitudes is. And then the trough to trough, you get extra deep, whatever the sum of the 2 amplitudes is, and it's negatory below sea level. But if you get trough to peak, at some point, and if you travel, a square mile of ocean where these wave sources interact, you're going to see a million flat destructive interference locations, and you're going to see a million maximum constructive interference locations. They're going to be all over the place. But when you find crest and trough together, you don't get a wave for just that instant of time at that location. And the waves are moving. So that flat water, it's actually as if the flat water is moving from left to right or from right to left, or in some direction. Now here's a picture. Can I move this now? No? Okay, this one time I'll let you guys copy from the display. Of course, it's all going to be in YouTube, so I can't believe I forgot to move that, though. See, Brittany, I was already on that here on my screen. I know, and this is, I got caught napping. It's pretty bad. It's not even Monday, and I got caught napping by myself. No, by a student. All right, so here's a picture. Let's keep going. Now, here's wave A from Nova Scotia, wave B from the coast of West Africa. And the second image, A plus B, adding up, there's your rogue wave. Somewhere out in the middle of the Atlantic. And this is a snapshot. And what we would say here at this location is that these two waves at this location, at this moment in time, they are in phase. All right? And after they interact, they just keep on a going. The other one's heading up towards Nova Scotia. The other one's heading down towards the coast of West Africa. All right? We call it constructive and destructive, but nothing gets destroyed except the height of the wave. All right? So they just keep on a going. They go through each other. It's kind of like quantum tunneling. Did I say quantum? Yes. We're getting close to the periodic table, my friends. Now, here's destructive. Now, we've got A and B, a different A and a different B, and they're moving towards each other. Now, when these two interact, A plus B, you get zip, zap. You get flat water. You get fishes under the sea, but that's it. No Sharknado here. All right? And what we would say is they're 180 degrees out of phase. All right? Because one's a peak, one's a trough. And those are 180 degrees out of phase. And this is from two different sources. So this one's going to have, and these are kind of simplified, idealized. We don't have peaks and troughs going through here. But your homework coming up over the weekend, you will. I have some well-designed pictures. So these ones, you get flat water, destructive interference, but only at this position and only for this instant of time. Now, so this is, the top image here is before interaction. The bottom image here is during interaction, destructive interference. And now the third image here in the middle is after interaction. They just keep moseying off to where they were going to start with. All right, Connor.
How long is that interaction time-wise?
It doesn't have a duration. It's an instant of time. So you're going to see it. If you take a photo, you'll see it. But if you take a video, you'll see a little bit of wave and then flat water and then a little bit of wave after that. If you keep it aimed at the same point in the ocean. All right. So that point in the ocean, basically what it's going to do, it's going to go from, these are not true ocean waves because we're only looking at dips and bumps, but not a train of dips and bumps together. If we were, you'd get alternating between flat water and rogue wave, and then rogue dip, and then flat water, and then rogue wave, and then rogue dip. Okay? So, and then, of course, ocean waves are three-dimensional, so it's, this is kind of an idealized picture. Now, I want to give you a head start. Oh, I was going to do a demonstration up here with you. I'll do that on Thursday. Another interference effect that's important to know about, and that's called beats. B-E-A-T-S. So we're not talking about the headphones. We're talking about beats. So what happens is if you take two different wave sources and they're slightly out of frequency, slightly different frequency, slightly different wavelength, like these two up on top, they'll add together and you'll get some flat water and then you'll get some rogue waves at a different location. So this is constructive over here on the left, and then down here you get pretty much flat water. And then over here you get some constructive. Now, this is a picture from an old textbook. Here's my picture. All right? Now, all you got to do is look at this and think. These two waves, slightly different frequencies and wavelengths. Let me give you the specs. All right, so we got sea level through the middle, and let's just call it equilibrium because we're going to talk about them as sound waves. And let's give it a phony propagation speed, 80 meters per second. So go ahead and write that down. You can calculate everything for this. All right, now, I set this up on my spreadsheet and graphed it up real carefully. 106.7 hertz for the top wave, and then just a little bit higher frequency. So these would be pretty low notes. They'd be bass. All right? Now, F subscript B is the difference of the two. F2 minus F1, and that's called the beat frequency. Now, here's what that means. This is what you'd actually hear. You'd hear the sum of the two. The black and the red would look like this blue wave train. All right? And so you'd hear, if you're listening to two sources, slightly different frequencies, slightly different wavelengths, you'd hear some loud over here. Look at that, high amplitude, rogue waves over here. And down here in the middle, that's your flat water. So you got a little bit of amplitude, but it's kind of pokey. So that would be faint. And then you're oscillating back up to maximum amplitude over here. All right? So this is an accurate depiction of how beats would. So if you could look at your auditory nerves, these would be like this blue curve is like the nerve signals that would be going into your brain. And what you'd hear is a kind of a buzz. And I'll demonstrate this beat, the buzz that you get on Thursday. And in this case, the buzz frequency is 12.8. That's a really low frequency. All right? Now, I'm going to stop here, and we'll finish this on Thursday and then start electromagnetism. Oh, by the way, I'm trying to get mini review 6 and 7 activated. They're supposed to be due next Tuesday, so hopefully they'll be activated sometime today. So keep a look at that, and you can. And otherwise, no homework. You're dismissed.